So we stopped class in the middle of this problem yesterday. We were taking and trying to figure out what is the maximum volume, and we had found out the dimensions of that box. I know some of your classes actually got a little bit farther than this, but let's just go ahead and we're going to pick up from right here. So let's identify the domain of the function. So when we're talking about the function, we're going to be talking about the entire graph. And so when we're talking about the entire graph, we're talking about everything that we can see and what we can't see, where it continues on to. And so at that point, we're never going to have a time where we're not going to cover x. And so therefore, our domain is going to cover all reals. And so remember, when we were talking about domain, and this is going to be done with a function, we're covering all reals from negative infinity to positive infinity for domain. But we have a story going on. So when we take into account our story, we have to consider what is that y standing for. And so when we consider what that y is standing for, we realize that we really can't have any of this negative down here, nor the negative down here. So that's really going to restrict our domain from 0, which I'm going to go ahead and put a little bit farther into this so that we can actually see it a little better. Actually, no, you should be able to see that one fine. Let me go ahead. And then to 6. I know part of that cuts off, so I wanted to let you be able to see the whole thing. So from 0 to 6 is really our domain. So our domain for the story starts at 0 and goes all the way to 6. But at 0, my volume is 0. Are we going to design a planter box that has no volume? The answer is no. There'd be no point in it. And at 6, our volume is 0. Are we going to design a planter box that has no volume? No again. So therefore, we're not going to include those. We're going to put those in parentheses. And so remember that our domain is all the x values that would work. And so for our story, that domain is from 0 to 6. Well, the reason I did include, as you notice, there was a time where it went ahead and went back up. I didn't include those values, even though it's a positive domain or positive volume, because they are starting to become repeats of some of the ones that we previously had. And we really can't have a situation where we have 9 inches for the height, because then we don't have any object left to take that 9 inches from. And so those really get off the chart because of our product that we're dealing with. And so we are sticking between 0 and 6. Because otherwise we don't have any product, and just because two negatives multiplied to get a positive does not mean that we really have a volume. And so that restricts our domain down between those two spots. Now let's think about what is our range. Well, when I look at the graph, the entire graph, and I'm going to go ahead and zoom back out so we can kind of see the whole graph. It's going to continue to go all the way down. It's going to continue to go all the way up. And so range is going to continue on forever in the negatives and forever in the positives. So we have an all reals situation going on with our range as well for the function. So the function continues on forever, both in the negatives and the positives. That means that at negative infinity is where I'm going down to for the negatives, and a positive infinity I'm going to up for the positives. But if I actually deal with my story, My story doesn't really cover all of that. My story is wanting to come up with a volume for those planter boxes that's restricted to the materials. So I need to be positive. So if I need to be positive, the lowest I can go for my range is 0. Excuse me. I'm not including 0 because would it make sense for me to create a box as a volume of 0? No. But I need to figure out what my highest point is that I can go to. So when I look at my graph, and I'm going to go ahead and zoom this back in so we can kind of see what's going on between 0 and 6. And I'm going to go ahead and bring this back down to where it's looking at just the 400. And then I'm going to go ahead and give it a little bit of room in the negatives. But let's do a negative 100, just to give me some things to see below. I'm really restricting it to here. So that highest point that I actually will get up to is going to be that 228.16. And I know it keeps on going on, but we will go around it to there. And so I'm going to stop at that 228.16 for my maximum volume. But can I actually be there? Oh, I can. So let's go ahead and take it and include that value. So I can actually create that maximum volume. So that's the reason that one's going to be a square bracket. So again, this is for our range. And when you're considering the story, we have to consider the constraints of the materials that we are using. So what are our x-intercepts representing in this situation? So let's look at the graph. My x-intercepts are here and here. And I know that there was another one in the function, but we're going to really focus it into the story area. So those are the 2 points where my y value is 0. So my y value is the volume. So those are the 2 times, so the x-intercepts are when the volume is equal to 0. So we've talked about that. Does a 0 volume make sense in our story problem? No, because we don't have any time that you're going to make a object, a planter box, with a volume of 0. So when we're dealing with this, we talked about other things. And so let's talk about that relative maximum. That relative maximum is the highest point we can get to. We also have a relative minimum, which is our lowest point. Those are not the absolute min and absolute maxes because there are times where the graph is going to be below or above. But we had they ordered a particular planter box with a volume of 100. So that means we need to take and find where in my volume is it at 100. So our volume is at 100 when y is equal to 100. So I'm going to go ahead and drag that down. And you can see that there's going to be well, actually, technically, there's 3 different locations. That's the case. But we really aren't concerned with this one over here because it's outside of the story. So it's not dealing with the story. Once we pass here, no longer does anything else deal with the story. And does the same thing as over here. These don't matter to our story. And so let's look at the graph. And this is where you can use your calculator to help you. And you're going to type into the y equals 100. And we need to find the intersection. So those are the two intersection points. And so we have the two intersection points of, oops, I'm going to drag my graph around. .541, 100, and 4.761, 100. And so if we were to write it, the question asks us to write it as the using function notation. So what that means is we're going to use it in this type of format. And so we have v of 0.541 equals 100. That's that function notation for that ordered pair of 0.541, comma 100. That's the same thing. And so for our next volume one, we need to look at it for that 4.761 equals 100. So what do these intersection points mean? That's when the volume is 100, and that's going to be our height for when that happens. And so we can make two different planter boxes. One is going to be 0.541 as our height. We need to figure out what our width and length are. And our width is 12 minus 2h, and our length is 18 minus 2h. And so when we do that, we plug those numbers in. We come up with our two different volumes. And that means that we have that it's going to be a, let me see which one it was. Sorry, look at my numbers. So that means that we have a I have sorry, I was going too farther in this question than we needed to go, but we'll be looking at this scenario. And so we'll be looking at that's only a half an inch deep. And then there's another one that's 4.761 deep. Which one makes more sense? Well, it depends on what you're planting. So what you're planting decides whether you want this one or that one. Which one makes more sense? So succulents might plant well in this case. But something that needs a deeper root system, you're going to need a little bit more to work with. So now, I want you to think through what would you do to create this one. You want it to be 175 cubic inches. So when you did this, that means you need to change this from 100 to 175. So that brought us up a little bit. to those two locations. And again, we're not worried about the other one because it's off of the situation that's possible. So we have those two planter scenarios. And so I could create it where the height is equal to 1.15 but to get my width I need to do 12 minus 2h. So my width is 12 minus 2 times 1.15. And so when I do that math, my width ends up coming up to 9.7 inches. My length is at 18 minus 2 times my height. And so I come up with 15.70 or 0.7 inches. So now let's look at the other scenario. So the other scenario, we take that same information, but we're now going to be using the other height. And the other height option we had was at 3.78. So our height would be 3.78 inches, making our width 12 minus 2 times 3.78, which gives us a width of 4.44 inches and a length of 18 minus 2 times 3.78, which gives us 10 and 44 hundredths of an inch. And so those are the two different planter boxes the company can create for the committee. The base is length times width. So we know that length times width is equal to 12. Now we got to figure out what can I do in order to take and make out the information. We're going to have to go back to our graphs. But that's not going to really give me my area. So what part of it's the area? Well, that's the area. And I know it needs to be 12 square inches. So I need to look and see what's happening at 12, whenever y equals 12. Well, I find out these are my two possible locations. So that helps me find my height. So height would either be .21 or 9.8. So, but the problem is that 9.8 doesn't make sense in our story because that's greater than 6. So really the only one we have to work with is a height of 5.21. Now to find our length. So remember length was 18 minus 2h. So in that case, it means 18 minus 2 times 5.21. And that means that we have a width or a length of 7.58 inches. And our width is 12 minus 2h. And so if we do 12 minus 2 times 5.21, that gives us 1.58 inches. So there's our length and our width. And so our volume is equal to 5.21 times 7.58 times 1.58. And that gives us a volume of 62.30 cubic inches. And so that gives us all the possible dimensions, even though we didn't have enough to completely come up with it. We can use a graph to get us here. Oops. We just had to think about it in a different way. But what would you say to someone? They want to have a height of 5 inches that would hold 100 cubic inches of dirt. And if we look at our chart, 5 inches would be here. And so the max it's going to hold is 80. So 5-inch height will only hold 80 cubic inches of dirt. So with what we have, we can only create the maximum of 80. So we need different materials. So now let's take in, we're going to be looking at Plant a Seed Company. And they make cylindrical planters for sidewalks and storefronts. So volume of a cylinder is pi r squared height. And we're going to be dealing with some variety of sizes, but all have a height that is twice the radius. So height is equal to 2 radii. So why would they want to come up with that? I want you to go ahead and answer that question. Why? And so when you finish that chart, so your table should have filled in like this. So now, how can I find, if I am given a particular volume and I need to go back, how can I go back? So if we're given the area and the height, you can easily get the volume. But we want to figure out how to determine the base area and height with a given volume. How could you do that? You could say you could graph and find, but we need to have an equation. So what is our equation? Well, we said that the height is 2x times our area of our base, pi x squared, and that gives us what we can graph. So when I go to my graph, I want to look at it. Well, if I notice, and I kind of kept the same window area, it wasn't quite exactly the same. But here's some getting into it a little bit farther, like what we had last thing we graphed, looking at from to 100. As I keep zooming out, you notice it keeps going up, and it never comes back down. It never has that extra hump. And so if I look around, I see that I'm continuing to go up. And so you could take and find what's happening at 2,000, at y equals 2,000. I was off my graphs. Let me go ahead and zoom out to where my y's are going to go all the way up. I'm going to go ahead and do 2,500 just so I can have enough for me to see. Oh, that didn't give me enough for my x's, so I'm going to move it around. And you notice how I'm not doing zoom out, zoom out, zoom out, because it causes you problems. And so I find that 6.828 is the number here. So 2 times 6.828, and I'm just going to call that 6.83. Just for our ease of work. And that gives me 13.66. So pi times that 6.83 squared gives me 146.47. And so if we keep on, every time we increase the radius, the height doubles. The area of the base times 4. And then the volume, what am I multiplying by there? Volume is times 8. So we're going to go ahead and graph it we're going to find these three things and graph them on the coordinate plane. So you can use your graph. And so the coordinate plane is from negative 2.5 to positive 2.5. And then on our y, we went from negative 5 to positive 5. And our step was 0.5. And our step here, oops. So this is our volume. Our height is 2x. And then our area of the base is pi x squared. And so we're going to graph this here. So when we're looking at these two general shapes, we find that they are both having a positive slope, and the other one's having the positive slope. We all have the same x-intercepts. But, and so we have, they're both increasing, they both have the same x-intercept, and decreasing over the same area. Now,